a story. We were talking yesterday about Newman projections, which are conformational isomers, all right, of straight chain alkanes, like this guy. He's just a simple. By the way, you have at the bottom of that paper. Do you have the cyclo ones yet? No, probably not. Right? You just finished that paper up, right? Or do you have them on the bottom? What is the last thing I see? Some. Well, I just said that. You said no. The cyclo is on the bottom of that paper, right? All right. Okay. It's called reading. All right. Now, if you look here, this is looking at them sideways. I can see this compound is ethane, but I can't really tell what its conformation is. So I have to draw them like this, and that's what I showed you how to do yesterday. Hopefully you got that done. Hopefully you did your worksheet. I'll collect that in a little bit. We'll look at it. I'm also going to have you do another one today in a little bit, using Beaker to help you. Yes, Beaker will actually do these. It will draw them for you like one or the other. Bailey, I am going to rip that up. Put it away. All right. Now, Beaker will actually do these for you. Okay? It will actually do these, draw them for you, and name them for you. So you'll be able to check your answers today on the new worksheet too. But today, before we do that, the new stuff I got to show you is this. Okay? So you're all looking up here? This is the new stuff. When you have a cyclo compound like this guy right here, okay? What would this guy be, by the way? Cyclo what? Hexane. All right, everybody looking at this? Cyclohexane. Okay? Well, turns out you can't rotate these guys all the way. I would break the compound. All right? They only have limited rotation, and they do have some limited rotation. So here are the two conformations. This is called the boat conformation. As you can see, it clearly looks like a boat. And then let me put him into the chair conformation. And there's a chair conformation, which obviously is a chair. So you can't really have any questions on that. That's pretty simple, right?
Right.
Yeah, exactly. Which is why I wanted to show you this program, which is the only time I use it once a year. And that's where my story comes in later on. I'll tell you my story about this program. But yeah, it's very hard to see, especially depending on how you look at it, whether this is a chair or a boat conformation. It's a lot easier if I could show it to you on a model on the board here. So that's what I'm going to do. All right, and I'll show you how they both look different, and they both have slightly different properties. All right, let's take a look. If this works, which that's what the story's about. All right, turn on my projector. Might want to turn off that screen, that light there. Now, again, when I first see this come up, which hopefully we will, you'll see that it's just the way I was holding it before. When I hold it, you know, in the plane where it's facing you like this, like that, all right, when you're holding it like that, the molecule, it's hard to see what kind of conformation it is because I can't rotate any of these bonds all the way around. But they are actually partially rotatable, that's a word. And let me show you, if I put them a different way, what it might look like. I'm going to rotate him on the first on the x-axis here, and I'll get him to a spot where I can see it better. All right, right there. Okay. Now I'll rotate him a little bit up on the z-axis. There. And now.
The following homeroom should report to the auditorium for pictures. The cafeteria study hall should go. This films room 2 and room 5.
Okay. Now, watch as I rotate this guy, and I'll be stopping him. You'll be able to see the difference between them in a little bit, and why one's called a chair and one's called a boat. You ready? As I rotate these around, all right, I want to stop it right about there. All right. Now, the reason this is called a chair conformation. Yeah, well, actually, I can probably flip this guy down a little. It's kind of like one of those lounge chairs, like those chase lounges you would have maybe around a pool. So, like, you'd be sitting here, and that's the back, and that's the feet. Okay. And this guy right here actually is the more stable conformation. Because if I rotate, he looks kind of like a chair. Let me pull up the boat, and I'll show you the difference. Keep that picture in your head. Let me pull up the boat and show you the difference. Oops, I have to. The boat, again, when I first pull them up, oh, I don't want to have both. I want to have a new one. All right. When I first pull up boat, and I have to scale it down a little bit. I can't tell the way it looks there. And I'm not going to do that to you. I'm not going to put a guy on here who can't really tell. But if I spin him into the right position, and pause him right about, well, And now I'll just rotate it around the y-axis a little bit, and you'll see the difference. Ah, you see it? Last one, this little guy down here, where was he? Remember I said it was like a chair, like a chase lounge. The back, the seat, and then that was down. This guy's flipped up. Now here's what that means. When I go and rotate this guy, I'm going to put him directly in, I want to rotate around the y-axis here. But I want to get him exactly even. So I'll probably flip the Z up a little bit. Nope, that's not the one. Well, I needed to do that one. So. Oh, look, it's upside down boat. That's the kind of boat like an old Viking boat. You know what I'm saying about? That's why it's called a boat. And I didn't make these names up, by the way. Too far. It's coming around. Around. It's coming around. It still went too far. It has to be perfect. It doesn't have to be perfect, but I want it to be. Yeah. That's good. Now, on the Z, no, that would be the x-axis. Flip them up a little bit. There we go. Now, watch. You can tell which one's going to be more likely to be stable. This guy, when I stop him right there, see these guys down here? What are they? What are the hydrogens from yesterday? They're eclipsed, exactly. All right, so if I look at those guys, they're directly eclipsed. All right, now you'll come around, you'll see the other ones. I can do that to almost any one of those bonds. If there's another one, see it again there? They're basically eclipsed. But if I were to show you the chair conformation, I'm going to have to quit out of this. You'll see that they aren't necessarily staggered, but they're as staggered as they can be. Watch for the chair conformation. And again, I got to scale it down a little bit. All right, I'll rotate him, spin him. Got to bring him out of here so he's not in the way. Pause him right about there. And now, when I rotate him along the y-axis, and maybe up a little bit, yeah, up a little bit on the x-axis. And bang. See these guys here? Looking down the bond now, what do you see? Pretty much as staggered as they can be. So it turns out the chair conformation is a little bit more stable than the boat conformation, okay? Because of that. And they actually flip back and forth into both conformations as well. Now, one other reason I want to show you this, we make these models all the time, and we use sticks. All right, we use sticks and balls. It's called a ball and stick model. But I wanted to show you something, because you have to realize something that it's pretty impressive when you're not really thinking about it. But there's other ways I could do this same model. Okay, there's a ball and stick too. It's called. It's just I don't know what that does really. This one is kind of cool. Isn't that neat? That's kind of neat. So you can kind of see through them. If I were to rotate him, one way or the other, I could rotate him. Oh, that makes him bigger. Oh, that's neat. Huh, I didn't know you could do that. That's cool. How about this one? Oh, look, he rotates. Pretty neat. All right, but the one I wanted to show you here, here's a Spaceville one. That's the one I want to show you. You see, in reality, we draw these guys with sticks and balls, but they're really right on top of each other. These electrons are overlapping. If I showed you that dog toy, it's like no way you'd be able to tell probably whether that's a chair or boat conformation. But you have to remember, that's how close they really are together. All right? So, such that it really does make a difference. Turn that light on for a second. Like if in the chair conformation, which now maybe you can see. Can you see how that's a chair now? This is the back of the chair. That's the foot of the chair. If I rotate him like this is the seat here. And if I flip this guy up without breaking him, all right, I'll get the boat. All right, you get the boat conformation now. You see how it's a boat, right? Okay. All right. Well, the thing is about this, these guys up here at the top, you can see from the Spaceville, they're practically touching. And remember, they want to repel each other. So this is the least stable, not just because, as I look down any of these bonds, they're actually eclipsed here. But these two guys at top are as close together, as opposed in the chair conformation, they are as far apart as they can get. Okay, because the guys flip down. All right, now, all of that's well and good. You might say to yourself, well, where does this ever come into play? It actually does. All right, I'll close this guy out here. Oh, wait, that has another way to do it too, by the way. A couple of others, but that's the one I wanted to show you. There's pipes. You may buy a model set when you get to college that'll look like that. Instead of with actual balls, they'll have just sticks with different colors. The constellation. See that one? Like, it looks like a constellation. Yeah. Textured. This is kind of cool. Turn that light off for a second. That's kind of cool. And I could even letter them. So you tell what elements they are. Carbon, hydrogen, okay? So it's a pretty cool program, and I use it exactly once a year to show you this, because most of the time, and there's a lot of other chemical compounds I can put on here, but, you know, we, most of the time, don't meet, sorry, I don't want to say, hit the wrong button there. But look at all the different things that this will draw for me. Some of the amino acids I wanted to draw, if I wanted to. Here's asparagine, okay? And it will tell you what the compound for that guy is. Or glutamic acid, or leucine. I knew leucine. No, I'm just kidding. Leucine. All right, so that is MoluCAD, and that shows you basically what I wanted to show you. No. All right, is that light back on? I said no. I said no. No. Jeez. It's a very old computer, which kind of brings me to my story in a little bit, but I need to give you the notes first. Bottom of that page. Okay, I got to shut this off now. Bottom of that page, we're going to talk about cycloalkanes. And as you already know, these guys are ring structures, and therefore they only have a limited rotation about the carbon-carbon single bonds. They can't rotate all the way. I mean, think about it. I can't take this guy and twist that bond all the way around. It's going to break the ring. See? Told you. Nobody listens to me. All right? So they only have a limited rotation about the carbon-carbon single bonds. And I need to show you the two extremes. There actually are twisted boat, and there's a couple of intermediate steps between these guys. But I'm just going to show you the two extremes of the boat and the chair. And again, a lot of people think I make these things up. I don't. If you look up in an organic textbook, you're going to find the words boat and chair to describe cyclohexanes to conformations. I didn't make that up. All right? So think of the boat and the chair like this. Okay? Your boat is kind of like, it's going to look like that. And your chair is kind of like one of those lounge chairs you see around the beach or around the pool. Okay? How do we draw them? Well, don't you try. I'm going to show you how to draw them in a minute. But that's basically how we're going to draw them. Don't try it on your own. I'll show you a little way to do it. You're going to make the skeleton here first for the chair, and then you'll fill in the H's and the C's. And I'll tell you, we actually don't have to write the C's, because we know in every individual verticide there's going to be a C, right? Okay. The boat would look like this. Same thing. We'll make the thing for the boat first, the actual skeleton for it, and then we'll fill in the H's correctly around it. All right? Let's show you how to draw those. All right? Let me show you how. I'm going to actually go back to a black background because it's easier for the camera to see if anybody's absent. Okay, so underneath cycloalkanes, you're going to have the chair and boat. We'll call the chair on this side and the boat on that side. Okay? Now, both of them have a little trick to them. And it really doesn't matter which way you were to make the boat, if you were to start from the bottom and have it facing up, or vice versa. But I do them usually like this. Can you make that? Okay, that's your basic skeleton of the chair conformation. It's not a very good one. I could probably make it a little bit better. Let me do that again. Yeah, it's a little better there. Now, here's a trick. There's a little bit of tricks for each of these. All right. You're going to draw in your what are called your axial hydrogens. All right, first, and I'm going to label these in a second. But they're the ones that face directly up or directly down, straight up or straight down. Let me show you with my model first, and then I'll draw them on there. I've got to twist them into the right conformation. All right. So there he is. Can you see this? I don't know if you can. But can you see how that is what I have up there? Okay? Notice that as you go around the ring, and remember, this is a ring. This is a ring. So go around the ring. Every other hydrogen is either up or down. Well, it should be either straight up or straight down. The model's not perfect. All right? So I would start with this guy down, up, down, up, down, up. So you put those in like that. Of course, the one facing down is from the guy at the bottom. The one facing up is facing straight up. One at the top one is facing straight up. Okay? All right. Now, the rest of these guys, because, if you can look at this, the other ones are all, as I rotate it, they're all coming, these what are called the equatorial ones, they're all coming out from the center. They're all coming out from the equator. That's why they're called equatorial. Okay? So that'd be out, 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 from the center. All right? So that's how you would draw those guys. And that is the chair conformation. See how you have to start thinking in 3D, okay, 3 dimensions. You got to do this. You have to be able to see. If I were to draw that for Mr. Phillips when he walks in here to make fun of me, he'll see, what will he see? I don't know. But he will see a ring structure that's in the chair conformation like you do, hopefully now. If I do a boat conformation, I draw my boat. I made that a little bit too big on that one end, but I'll just erase that. Yeah. Okay, here's my boat conformation. Now, in the boat conformation, your two guys at the top are facing towards each other, which is one of the reasons why it makes it unstable. Okay? The other guys are all facing out from the center, but unfortunately they're in the same. Nobody's in an axial or equatorial position. They're not straight up or straight down. Right? And remember how if I were to rotate this guy, these guys would be eclipsed. These two guys would be eclipsed. Okay, that's just facing up a little bit more. These two guys would be eclipsed. And if you were to look alongside of them, that's what would happen. And that's why this guy's less stable in the boat conformation. Because of the eclipse conformations along these axes, and because of these two guys up here being very close. Remember, as I showed you with the space film, in reality, there are no wooden sticks between these molecules, between these atoms. All right? There's no wooden sticks. They're really just overlapping orbitals of electrons. And therefore, when they get that close to each other, they really are repelling. They're not really too happy about it. All right, so here's the boat conformation. I'll flip it back up, and you can see it. All right, again, hopefully you can see this. Okay? These two guys at the top, very close together, not happy about it. And if I look down any of these bonds like this, these two bonds here, I see that they are eclipsed, right? Okay. All right, good enough. Well, we said already, I already asked you, which one do you think is more stable? Probably this guy is more stable. And this guy would be less stable for the same reasons. All right? Because of the hydrogen repulsion, due to the repulsion of the hydrogens. And I also need you to label the axial and the equatorial carbons. So what I want you to do for the chair is I want you to draw another compound. Hopefully you have room somewhere. If you don't, on the bottom, you can draw. I want you to draw something that's going to be up here in a second. And labeling them A and E. All right? You're going to redraw the chair conformation. Watch. Oops, sorry. Everybody got that? Good? All right. We're back to where we were here. Showed you that. That's what I just drew. That's the other boat one. Now, that guy's more stable. That's less stable. Axial versus, you don't have to write that down. Just draw this guy right here. There. That will be the one you want to draw here. Okay? A's, these are the axials or the up and down ones. So if you just draw in the middle somewhere, another chair conformation, but drawing in your A's and E's and labeling them as either axial or equatorial, okay, you could do that. In this one, I have the upper end here and the lower, this end's flipped down. It doesn't matter how you draw it. Same if you have that end down and the other end up, it's fine. Now, you may wonder, again, you'll probably, unless you go into real chemistry, unless you take a serious chemistry class beyond an intro chem class, you'll probably never see any of this stuff. I don't think you'll see any of this stuff on the AP exam. This is beyond the AP exam, just like the mechanisms I'm going to teach you are beyond the AP exam coming up soon. All right? But I remember I said this a long time ago. I always fought making this AP just because of the organic that you would lose if I had to cut this out. But because we have the extra time now, I feel I could do both, and we'll see if we can at the end of the year. If we all get 1s and 2s on the AP exam, I know that didn't work. Hopefully you'll get 3s and 4s, and that will be nice. All right? Because this kind of stuff, I'm wasting my time. And that's why other people who have AP Chem, like maybe in MMI or Scranton Prep or Wyoming Seminary, you know, these other AP classes, they're not going to really waste their time covering the organic that I'm showing you, right? Like here, trying to make you think in 3 dimensions. They're going to give you the basics of organic chemistry, maybe a couple of alkanes and alkenes and a few functional groups like alcohols. But that's it. They're not going to do a whole heck of a lot like I'm doing with these things, okay? You might wonder what this has to do with anything. Well, it turns out the position of these axial or equatorial, when you put, I can put things on this chain. Just like I can put chlorines and fluorines and methyls and ethyl groups on anything. And if I put things on this chain, where they are matters to whether they are going to react at that spot or not. Some are more accessible, others are less. I'm not going to go into that. That would be beyond even the organic I want to teach you. But it does matter. At least you have a terminology knowing these are axial and these are equatorial, and you've seen the chair and boat conformations. You know which are more stable and which are less stable. Okay? Good enough. All right. That's it for today, for the notes. But I have to tell you my story. You want to hear my story? Mm-hmm. It's a pretty good one. Oh, that's for next week. All right, hold on. I want a black background. Good. I need a black background because it was a black day yesterday. You want to hear this story? It was a black day. You just saw the class, all right? And sometimes you guys don't have any idea what goes into a class. Well, that was nothing. I mean, how would it take you 5 minutes to get that ready? This is an amazing thing. This is Murphy's Law to the nth degree. The program I just showed you, the one from the beginning of the class, is called MoluCAD. And I actually saved this computer because it's an old computer. Look at this thing. It weighs as much as an actual desktop nowadays. Okay? That's how heavy this thing is. It's a very old computer. It's probably about 15 years old or more. And the old versions of Windows will run this program because this program is about 15 years old. And I have the disk for it. I actually, knowing that I'm going to use this program every year, I saved 2 copies of it. I have this copy, and I have another one that's in here. It runs it. It needs it to run it. So I get out. I've done this for 15 straight years. I have absolutely done this every single year in organic for 15 straight years. Yesterday, 8th period, I'll set up my lab because I know it's a pain in the neck to do this one. Notice I've got a projector here as well as a projector there, and they have to overlap. So it takes me a few extra minutes to set this up, but it should take me, and it all goes well, 3, 4, 5 minutes to set everything up. I get my first one out. I hook it up. I plug it in. I turn it on. Turns on. The whole thing works. I got Windows showing. I get my disk out. I'm going to put it in there, and I put it in, and I go under the programs to run MoluCAD like you saw me do, and I turn it on, and it won't run. And so I try, okay, it says it needs the disk. So I eject it, put it back in, eject it, put it back in, and try some other stuff, work with it for about 10 minutes, can't get it to work. So I eject this disk. Maybe the disk is scratched. That's why I kept an extra one, I mean, I'm not stupid. I kept an extra one. I put the other one in. Go through all the nonsense. Nothing. All right, so for some reason, after 15 years, this computer is dead. It's not going to work anymore. So I'm not screwed because I thought ahead. I have another computer back there. You'll see it on that thing. And so I turn that one on. And I go through all the nonsense. I find, because these are so dead, I only use them once a year. I have to plug them in. You can't use them without the power supply because it would die. The battery was not around. So you plug it in. Power supply is dying on me because it's not plugged into the right thing. I screw around with that. I finally plug the first one in, put it in, won't work. Second disk, put it in, won't work. So now I've got 2 backup computers and 2 backup disks, and they all decided to fail for me on the same day. I've wasted about 20 minutes. But I'm not done yet. I go to Schrader. I say, Schrader, do you have any of these other Macs? These are a little bit newer. These are the Dells, okay? A little bit newer. Actually, I have the Dell too. I get his Dell. I bring it over. I hook it up. I have to put this in. But this time, I got to put it in, and I got to install the program because it was installed on the other ones. I'd done that years ago. Well, this is an old computer. It takes 5 minutes to install the thing. There's a little bar going across. Okay, I do all that. Turn it on. Okay, it's working. I actually show it. He's looking at that. Play with that. Great. All right, this thing's going to work. But I see at the bottom, little thing at the bottom. It says, plug in your power supply because your battery's almost dead. One of those warnings. But my power supply is plugged in. It's just a bad one. I look on it. There's an X on it. Mr. Rochford told me the ones that have X's aren't good. So I have to unplug my power supply and go get another one. And the time it takes me to do that, when I get back, the battery dies, and I have to restart the whole thing all over again. No kidding, not exaggerating this. Restart, do the whole thing over again, I hook it up. And then I plug in my projector, which was working fine. Turns on, projects to the board, and in 3 seconds, the projector dies. Swear to God. The projector dies. So I turn the projector upside down, and I am taking screws out of the projector at this point, looking for, it felt really hot, probably overheating. Fool around with the projector. At that point, I have no more time. It's an hour I have wasted setting up this class. So that's what went into that 5 minutes that I was using MoluCAD was 1 full hour of prep for that. No kidding. I'm not exaggerating that. So sometimes you guys don't quite see all the stuff that goes into the background. Not to mention, by the way, all those pictures and everything that are on there. They were there from years' worth of stuff, putting them up there, chair and boat, just popping up and all that other stuff. It is the equivalent of, and the only way I can use it to analogy for this, I think that would work for you guys. It is an equivalent of, you own 4 cars. And you go out in the morning and you turn the first car, you have to go to work. You turn the car key and the battery's dead. So you go to your next car and you have 4 flat tires. And then you go to the next car and it's on fire. And then you go to the next car and it's been stolen. That's the equivalent of what happened to me yesterday during 8th period. It was absolutely incredible.